Hello. How's it going? Good, good. Hey, we're going to talk about differential equations. So a couple things we need to know before we move forward with differential equations. Or one thing is, what are they? And differential equation, as it says right here, it's just an equation. It's got a derivative in it, like this one. It's a fairly simple form of a differential equation, but there it is. So what are we trying to do? Well, we're trying to find the original function, trying to find out what did we start with if this was the derivative. If y prime equals 2x over y is the derivative, what equation do we start with? And then hopefully we'll be able to answer the question, how do we do it? Well, I guess that might be what we were after. I was thinking that said, what do we do after that? But how do we do it? So how do we do it? Well, we do what's called separating the variables. Okay, and separating the variables is as simple as it sounds. You separate the variables. Get a pen. Come on now. Pen. There it is. All right, so when we separate the variables, we want to think about dy dx, that's what y prime is, equals 2x over y. Okay? To separate the variables, we're going to try to get our y's on one side and our x's on the other. So if I multiply both sides by y, on this side I'll have y dy, and if at the same time I multiply both sides by dx, on this side I'll have 2x dx. Okay? Separate the variables. Get all our y stuff on one side, all our not y stuff on the other side, and then we'll integrate. So we'll integrate this side, and we'll integrate that side. The integral of y is y squared over 2. The integral of 2x is 2x squared over 2, or just x squared, and we'll add a constant. Okay? And we'll add just the constant to one side, because if I add a constant to both sides, it's the same as, if I add 2 to this side and 5 to that side, I might as well just add 3 to one side or the other. Okay? So then ultimately, what we might end up doing is multiply through here by 2, perhaps? Yeah, let's do that. Let's multiply through by 2. I'm just going to call this C1. So then if I multiply through by 2, I get y squared equals 2x squared plus a different constant. Okay? And then I might just try to solve this a little bit further out, make it negative 2x squared plus y squared equals a constant. Okay, and that might be the equation that I started with to end up with that as a derivative. Okay? So, when we're talking about exponential growth, dy dt is equal to ky. Okay, what that's saying is that the rate of change of y is proportional to y. So how y changes over time in this case is proportional to y itself. Okay, so if we look at that, we want to get, that's a differential equation. We want to do the whole separate the variables thing. So we'll separate the variables, and the first thing we'll do is we'll divide both sides by y. So this turns into dy over y. And while we're doing that, we'll multiply both sides by dt. So k dt. Notice that we, take the denominator of our differential, of our derivative, and put it on the other side, and then the numerator we leave alone. Okay, we can integrate both of these things. The integral of dy over y and the integral of k dt. The integral of dy over y is the natural log of y. The integral of k with respect to t is k t plus c. We're going to call it C1 because it's going to change as we go through. We don't care what the natural log of y is. We care what y is. So in order to get rid of that natural log, we do e to the. Okay? E to the natural log of y is just y. E to the kt plus C1, okay, that would be sort of like e to the kt times e to the C1. Okay, remember what we can do with exponents when we're adding them together. Right? If we multiply e to the kt by e to the c1, it's just e to the kt plus c1. So e to the c1 is just a constant. It's just some number. We don't know exactly what it is. So we tend to write this equation in the form c e to the kt. Okay, which may look familiar to you. It looks an awful lot like PERT, but it's spelled differently, but same idea. Okay, it's our general equation for exponential growth. Anytime we have exponential growth, it works along this lines. Okay? All right, continuing onward, we want to find an exponential function for y equals c e to the kt that passes through these points. Okay, so this would be my t value, and this is my y value. T value, y value. So what we're going to do is we're going to use that y equals c e to the kt, and we're going to use the information that we have. Okay, for the first case, 1/2 is equal to c e to the k times 0. Okay? K times 0 is 0. E to the 0 is 1. So we have 1 times c is a half. So it turns out in this first equation, we just get that c is equal to a half. So now my equation looks like y equals 1/2 e to the kt. We've gotten one piece out of the way. So we use our second point, the fact that when t is 5, y is 5. 1/2 e to the k times 5. Okay? And so we're going to try to let's basically get e by itself. We're going to divide both sides by a half, so that means that we're like multiplying by 2. So we get 10 equals e to, I'm just going to rewrite this as 5k. And then we'll natural log both sides, natural log of 10 and the natural log of e to the 5k. On this side I get the natural log of 10, and on this side I just get 5k. If I want to know what k is, I take the natural log of 10 and I divide it by 5. If I had a calculator someplace nearby, I would grab it, and I'd come back and I would stop yelling, and I would quickly figure out what the natural log of 10 is, and then I'd divide that by 5, and I'd get k is 0.461. Roughly, you can verify that if you like. K equals 0.461. And so my equation is y equals 1/2 e to the 0.461, that's 6, 1, t. Ta-da! All right, onward we go. Newton's law of cooling. It says that the rate of change of temperature of an object is proportional to the difference between the temperature of the object and the temperature of its surroundings. So take a second and take a stab at what an equation would look like that represents Newton's law of cooling. Okay, so pause the movie, write something down on your notes, write something there, and then only when you've actually written something down, then you should unpause the video and move forward to the next slide. Okay, I'll wait for you. I'll be there right when you unpause. Seriously, pause. Did you do it? Okay, moving on. Hope you stopped. All right, so if you did that, and you came up with something like this equation, which, maybe it's right in your notes and you just looked at it and went, oh, it's this. Okay, the rate of change of temperature, that's this part here, dt dt, d capital T, d little t, is proportional, k, to the difference, that's subtraction, between the temperature of an object and the temperature of the surroundings. Okay, what we want to do is we want to be able to turn this differential equation into its actual equation. So we're going to do the old separate the variables trick. So it's going to turn into dt over t sub 0 minus t sub s equals k dt. We're going to integrate both sides, like so. And this is going to be a u primed over u situation because temperature of the object is an actual, is the thing that changes. Temperature of surroundings is a constant, so that's just going to be u primed over u. And so this side is going to turn into the natural log of the absolute value of t sub 0 minus t sub s. And this side is going to turn into kt plus c. Okay? And then we're going to use natural logs to free the whole thing up, like we did. So e to the, use e to do it. Okay? So this side just turns into temperature of the object minus temperature of the surroundings equals, and it's just going to turn back into that C, make that C1, C e to the kt. Okay, the same way it just did before, it's going to be C e to the kt. So the temperature of the object is going to be equal to the temperature of the surroundings plus C e to the kt. And that, my friends, is Newton's law of cooling, which we like to call NLOC. Okay, temperature of the object equals temperature of surroundings plus C e to the kt. Now that we've derived that from the differential equation, you can use that as we move forward to solve problems. Like this one, okay? Pointer, so I can get that back up here. Temperature of the object, temperature of the surroundings, C e to the kt. So in a room at 60 degrees, an object cools from 100 to 90 in 10 minutes. Question, how much longer will it take the object to cool to 80 degrees? So what we do is we know that the temperature of the surroundings, that's room temperature, is 60 degrees. And we've got some information that this is at T equals 0. This is at T equals 10. And so we use that to get some information for us. So temperature of the object at time equals 0, so 100 equals the temperature of the surroundings, 60, plus we don't know what C is, we don't know what E, oh, we do know what E is, we don't know what K is, and we know that T is equal to 0. We do some quick math on that. K times 0 is 0, e to the 0 is 1, so C plus 60 equals 100, so C turns out to be a 40. Okay, so now my equation, we know that C is 40. So we go with our second condition. 90 degrees is equal to 40, no, it's equal to 60, get out of myself, plus 40 e to the k 10. 10. Okay, subtract 60 from both sides, we get 30 equals 40 e to the 10k. Divide both sides by 40, I get e to the 10k equals 0.75. Through the power of natural logs, I'm going to get that 10k is equal to the natural log of 0.75, which I will quickly calculate for you. Negative 0.287. So negative 0.287. Divide that by 10, and I end up with 0.0287. So K equals negative 0.0287. I've got my equation. Now I just need to solve for time. Scooch a little bit over this way. We'll squeeze it in here. So we know, but that's really awful, negative 0.2080287. Too close. Let's try to back away a little bit. So now we know that the temperature of the object is 80 degrees, and that's equal to 60 plus 40 e to the negative 0.0287. You'll have to believe me that that's what that says. T. Subtract 60 from both sides, divide by 40. I end up with 0.5 equals e to the negative 0.0287 t. Natural log both sides, I'm going to end up with negative 0.0287 t equals the natural log of 0.5, which is negative 0.693. Where'd it go? Negative 0.693. If I divide both sides by negative 0.0287, I get 24. So I get T equals 24. Okay? Write that down, and then I'm going to ask you a question. So based on this, I'm going to turn this question into a multiple choice question. I think. There it is. So based on what we just did, those are your options. I want you to pick the correct option and record that on your paper so that we can talk tomorrow. NOTA means none of the above. So if you don't think it's any of these answers, then feel free to put that down. Okay? All right. Great. There's that. There's that. That's the homework assignment. Fancy, fancy, fancy. And we'll talk about that. Go back to that. Okay. Leave you with that again. And so multiple choice. That's what we know. Thanks for watching. Thanks for listening. Thanks for paying attention. And we'll talk to you soon.